Okay, so I'm going to present our work on how to simulate the heat equation on a dynamically crafted 3D shapes. So this project was done within a scientific project at bachelor level with my fellow students named here, and especially Gabriel, who is present with me, and also Damien, who were supervising us. So first of all, the introduction. Nowadays, most of the physical accurate simulation are made with meshes, and all of the PDEs are sold using some algorithm that needs meshes. But in order to do interactive crafting, meshes are not pretty decent because the operation like merging, cutting, and intersecting shapes are quite demanding for the mesh, so it's not really compatible with an interactive shape crafting. So that's why the game designer and the game programmer limited the forms used in the games and in the crafting. So the example of Minecraft is pretty obvious. Like there's only 9 square possible for crafting, and the reactions are mostly prescripted and like non-physical reactions. So when you want to cook something, for example, you just put it in the furnace and then it's cooked. So that's why our goal would be to let the player craft his own object. So for example, a sword. And when he puts the sword into a furnace, like the sword eats like a normal sword when you put it in the furnace. So the goal are interactive shape crafting, temporal heat equation, and also real-time interaction. We want this interaction to be playable in a game context. So, related works. Implicit surface are adapted to interactive shape crafting because it's quite easy to make 3D shapes with constructive solid geometry. And it has been introduced like a dozen years ago, so it was well known to be used in a graphics context, and also solving we mostly used primitives coded by Quiles here. Yes, and to the PDEs, solving PDEs not really needed mesh because there were a solution that was meshless that was invented quite a long time ago. So Vulcan sphere was one made by Nour like in 1956 to solve the Laplace equation. And this method is pretty compatible with the using of sign distance function because yes, it's really well adapted to this way of displaying the object. And combining both is not a new idea because it has been introduced to the computer graphics scene with especially Chen and Crane, who has published in 2020 this paper about a Monte Carlo approach. And then they have worked a lot on this, and they have published several papers to improve this method. So now let's present our approach. So we will use, as we said, a sign distance function to represent the 3D shapes. And we will use the Vulcan sphere approach to solve the Laplace equation. But but our contribution will be to modify a little bit this Vulcan sphere approach in order to make it transient, because like nowadays, they solve pretty complex PDE, but there's not the time component. So we want it to add this time component, and so we needed also to have a smooth cooldown. So we will explain this. So first of all, the transient adaptation. So our goal is to solve the heat equation. So the big equation on the top left corner. And to solve this, we use the directed boundary condition. So how shown is this picture is like we have several regions in the game. So one hot region, which is the heat source, so into the furnace, for example, and one cold region, like the hair, for example. And with this boundary condition, we have a solution, and we always can separate our solution into a static solution and into a transient part that converges towards 0. So the Woken sphere gives us the static solution. And for the transient part, we have to solve it. So using the separation of variables, we get several solutions of this equation. But due to the boundary condition, we have to sum them up in order to get the good boundary condition. So here is our first approximation. We only select one eigenvalue of the Laplacian. And our other approximation is to make an heuristic of this first eigenvalue because we want only to select the slowest propagating modes of the heat. So we took the length of the greatest bounding box of the object. And with all of these approximations, we get this equation just right here. So it's an exponential evolution towards the static solution. So in the context of moving an object into a furnace, T0, which is the initial condition, would be 0, and T plus would be given by the Woken sphere. So it's quite easy to implement this. But now when you want to retract your object in the air, there's a little problem because T0 is now the temperature before you have before the cool down, and T plus is now 0. So you have to save the temperature that was the one of the object before the cool down. And in order to save this temperature, we need to save it somewhere. So we used a little grid around our object. And each part of the grid was considered as secondary sources with an evolving temperature in order to mimic this cool down. So now I will show you the results. So here is, yes, you see it. Here is a video. So yes, when we put the sword into the furnace, it's heating, and when it's going out, it's cooling down. So we see that it's there's strays because that's due to the grid. So this prototype was made on Unity with this computer, and only the visible pixels are calculated because all of the computed equations are calculated on the CPU. And the result we get depends on the distance between the player and the object, and it's roughly around 10 to 20 frames per second, but several improvements could be made. And yes, a compromise should be found between the precision of the approach and the FPS, because it's a Monte Carlo method. So the more Woken sphere you make, the more precise is the solution. But the more Woken sphere you make, the slowest is the solution. So you have to make a compromise. Okay. So now let's focus on the diffusivity, because I was not explained it before, but there's a diffusivity coefficient in the heat equation, and we considered it as constants, but it's only constants in a specific part of the object. So you could put several materials with several diffusivity coefficients into a same object. So here is a snapshot of, for example, a complex object made of several bars with varying diffusivity. So on the bottom, the diffusivity is quite low. On the top, it's quite high, and we can see that the heat is propagating faster on the top than on the bottom. So this adds another layer of crafting possibility, because the player can select the materials he wants to use in order to make his object, and the heat evolution is going accordingly to this. So now let's compare the numerical result we get. So we compared our method on the 2D examples with the finite differences. We consider it as the ground truth. So as shown in yes, the temperature shown in this graph is the one on the green spot. So we can see that for the first frames, there's like a big differences between our result and the real solution. That's due to the lack of the fast propagating modes. But overall, after several frames, even if the result is noisy due to the Monte Carlo method, like the temperature is the right, is almost decent. So now let's conclude. So our work is essentially a transient solution for the heat equation on dynamic shapes crafted with SDF, and it's based on a modified Woken sphere method with a temporal adaptation using an approximation of the heat equation and a heuristic for the eigenmode. We also needed to adapt our solution to the cool down, and we saved the temperature on the grid to do this. So the limitations are, as seen before, the noisy results. Also, the implementation for use in real game is, yes, it's optimizable, obviously. And the heuristic approach is naturally adapted for spiky object, for example. So like boxing object, it's working very well for them, but I don't know, like a ball with spikes, it wouldn't work at all. And the diffusivity is here locally constant, so in each part of the object is constant, but it's not spatially varying. So improvements that could be done would be to remove the noise with caching and filtering, for example, and also to improve the accuracy using, first of all, more eigenmodes, so to develop more the approximation of the temperature, and also to have like accurate eigenvalues by solving the Laplace, the Helmholtz equation on the object. And in the context of video games, the temperature could be used to trigger some events. So, for example, a meltdown of metal, or even like if you want to merge to metal, like the merging of several metals. Or I don't know, if you want if you put your sword too long into the furnace, maybe it will bend. So that's another possibility. So thank you for your listening, and I will be happy to answer your questions.